Now we do. So a little out of. Okay. So that's the website. So what do you have to do, like really soon? Once you play a little bit with this, this is the announcement page. And so what do we have here? Welcome, blah, 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 blah. You can skip that. I would like you to register on Piazza. I hope that's set up. If it's not set up, it will be very soon. And the Piazza is going to be the forum for discussions online. We will not typically do the discussion by email about the content. Email, both me and the TAs, are for administrative issues. I'm late to that homework, I'm sick, I cannot come, I missed the exam. Please give me this, please give me that. I don't like my grades, you know, that kind of thing. If you have trouble with the assignments, what is that problem asking, and where is the data, and how do I get it, and how did other people get that result, that's all for Piazza. We'll do our best to answer questions at least once a day. I'm not sure if the TAs would be able to answer more than that, but before, you know, in the evening, they will get to the question and answer them. So that is the Piazza right here. In terms of submissions, we need you to, this is incorrect here. I need to change that. Don't share it with me. There is a Dropbox account for this class. So I have to edit this. I think the Dropbox account is, I have it somewhere. What you're gonna do is set up, most of you already have Dropbox, but if you don't have, it's extremely easy to set up. We want you to create a folder that is contain all the assignments that you have for the class and everything you want to submit, you know, like code. If you may, again, I'm not promised I'm not going to ask for reports, but every once in a while I'm going to ask for a short description of something, like a half a page, or for a plot that you have to plot and present the plot. All those things will go in that Dropbox folder, and you have to share that with us. Let me see if I can put it here. This is incorrect, so it's not virtualpavlo@yahoo.com. But I can find it here. I can't find it. So Dropbox, I'm just gonna write it here for now. Do not share with, I'll fix it right after the class. I'll put we have the account, but I don't know why it did not update here. So that's how you're gonna submit things. Now, you're not gonna get grades based on the submissions. You have to put the code in there. It's a requirement from university. I have to have an archive, some sort of evidence of submission from you of what you've done. But the grade you're gonna get after a demo at office hours. So you have to convince the TAs that your code works. It does what the assignment asks you, to do, and that is done by you. Now, I know people Google for stuff, and they sometimes take parts from different websites and forums to put it in. As long as you are in absolute control of what's going on, the TAs will ask you questions. What is this function does? How did you do this? Why did you get that? Where did you get that answer? That's okay. The way you should think about these assignments is just like you normally work in an environment. You don't come up with everything yourself. And in most cases, we're gonna be specific on what's allowed to use as a module. For example, more problems in here. In fact, I'm not sure the charger works, or that this even has power. Maybe not. Try this plug over there. So that's Dropbox. We ask you not to put data in Dropbox. So of course you're gonna have the data somewhere in your hard drive, and you're gonna run your algorithms on that data, and if you do the demo, you're gonna have access to the data. But if you put the data in, if every one of you puts the copy of the data sets in, that's gonna become a gigantic thing for us. So please do not put the data in there, just your codes, results, and everything else you wanna talk about. So you need to do that. We also want this student information. So in your Dropbox folder, we need this stuff. So I know you registered, the registrar has your email and your name and all that. I need to know what email address you want me to use. Some of you don't want to use the Husky address. You want the Gmail address. Whatever address you want to use with us to communicate, please use only one address. So whatever it is, put it here. Name, who you are, and why are you in this class. And then if you want to see your grades as the course progresses, we ask for a 5-digit ID. So you can there's be a database that you can, from the website, put your name and those 5-digit ID that only you know, and you're going to see your current grade situation. Okay. So this is a file that once you fill it in any format, you put it in your Dropbox folder, Virgil information or something like that, that the TAs can look at it and see who you are. Okay? Back to the schedule. So this doesn't yet quite work. We're gonna fill up more of this once we know the schedule. It's not settled. We have 2 TAs, and we are looking to hire the third one. We're probably gonna have 3 TAs. Their job is those office hours. So they're not gonna grade things, and they're not gonna do much other than being there with you, probably in the evenings, because they have other stuff during the day to talk about the code demos of the assignments. I'm looking to have office hours every day, Monday to Friday, but it's up to the schedule in the registrar to figure that out. Once it's going to be figured out, it's going to be announced here. But my plan is to have 3 hours a day of office hours where you again discuss the assignments to the TAs. Either to show that it's done and get the grade, or to get unstuck if you're stuck with something. There are 2 textbooks that are recommended but not mandatory. Every once in a while, I may ask you to read something from one of these textbooks, but my intention is for everything that's necessary for the assignments to do that in class. So my assumption right now is that if you come to class and take the notes or watch the video, you'll have 95% of what you need to do the assignments. I think those books, like everything else, are available via illegal PDFs, right? I'm required to tell you, don't do that. So I'm saying it out loud, do not use illegal PDFs. I know that doesn't matter in practice. it's fine. Some of them might be legal PDFs, by the way. There's some books that are putting the PDF online because they want people to have the book for free, and if that's the case, then you can have that. I think those are the basic textbooks for data mining. Again, I don't think it's required to buy them or to use them, but every once in a while we're going to have a read that chapter or that section from the book. And there will be some other books here listed as additional stuff. Yes?
That was regarding the homework submissions.
What?
Homework submissions.
Yes.
So you said that we are supposed to show the code to the instructor. So when the deadline is mentioned, is the deadline for submitting the code or is the deadline for getting the grade?
Right. So every homework has a deadline. So let's look a little bit at homework 1 on the schedule. Some links don't work, but I'll fix them. There's a homework 1 here, right? It says deadline 1/22. Is that about 2 weeks from now, roughly? Today is what, 8? Yeah, so 22 weeks. That deadline is when you stop the coding. So that deadline means you're supposed to be done by that deadline. Now you still have a week, about a week, to demo your code and talk to the TAs and see where it is. So it's not forever. It's not like you have the rest of the term to demo homework 1. But the deadline posted is at point where you freeze the code. That's what you've got. Now, I tend to be, like people know, lenient about those things. It doesn't matter to me so much that you finish by 11:59 on January 22. Okay, so that's not my priority here. My priority is to get everyone to do the assignment. If it's 1 day late or 2 days late, we'll have to negotiate some sort of penalty, but it's more important to me that you do it than that you exact by the time. Now, of course, you can't be late beyond, like if you are 3 weeks late with homework 1, obviously that's a problem for you and it's a problem for TAs. But it's better to talk to me in advance. Hey, I'm getting married on that day. Can you please give me 2 more days? Sure, no problem, okay? Right? Again, my interest in here is to get everyone to do those assignments. And about that, I can announce from the very beginning that I think the grades will be very high in this course. Because your main difficulty is not going to be in getting an A. I think most people will get A's. The difference will not be in grades. The difference will be how long it takes to do it. So there'll be people who get an A who spend 5 hours a week and they feel very relaxed. They go having fun all the time. And there are people who get an A who spend 30 hours a week. And they say, I got an A at the end, but I got killed. I haven't done anything else. I broke up with my girl, I failed the other courses, all of that, but I got an A in this one, right? So I do not, again, my purpose is to get everyone to do the assignments and understand what's going on, and I don't want to penalize you for being slow, okay? That's not my intention. Of course, if you don't do the assignments, you're going to get a B, or a C, or a D, or an F. Your grades roughly is going to come from these 7 assignments. I still have to decide the exam part. But, what? We'll see. I think there's a requirement for exams. There's not a requirement, but the university wants us to have exams. We may do one. I don't think you should worry that you think an exam may be harder than homework. I do not think that's true. I think some of these homeworks are harder than the exams that I can do for the data mining class, like we're talking about 2-3 hours exam sort of thing. I do not like exams because I don't think they test the right thing. If you are to be a data scientist and you go in a production environment and you are work on data, I don't think I can give you an exam at the end of the term on paper that reflects how good are you at engineering. So I think the biggest evaluation, in my opinion, is for people who finish all 7 assignments, aka got an A. The evaluation, if I would be a recruiter, I would ask, how long did it take you to do those 7 assignments over the course? If it took you, 30 hours times 14 weeks, 400 hours, then you're pretty bad. If it took you, 60 hours over the course of the term, then means you're pretty good. So I think the biggest difference is going to be the time you spend. That's the plan. And again, people who took IR with me, that was the similar pattern in information retrieval. Although these assignments I think are a little harder than the IR ones. IR assignments were time consuming but conceptually easier. This is a little bit more involved in terms of algorithm and C, but not as involved as machine learning. Now let me make a quick parenthesis for people who take algorithms with me. Just a very quick parenthesis. Algorithms, it's all about the lectures. Do not miss the algorithm lectures because 100% of your money, how much you spend on a course, $5,000? 6,000? Yeah. In algorithms, 99% of the $6,000, it's on the lectures. If you miss the lectures, you got wasted your money. Because everything else, it's on Wikipedia, okay? You don't need to take an algorithms class. The book is online, everything is online, all the problems online, all the solutions online. The only reason to take an algorithm class and pay $5,000 or $6,000 for it is to attend a lecture to get good explanations. Also, the algorithm class, it's all about the exams. Again, who takes the algorithms with me? Yeah, be prepared for real exams. Whoever gets an A in the midterm in the algorithms can get easily a job at Google. Easily. Okay? So those algorithms, the homeworks do not count for the grades. In there, the homework is just for you. You can cheat on the homeworks. You can find the solutions online and put them in. We don't care about that because the only reason for the homework in the algorithms class is to give you experience and preparations for the exams. The grades come from the two exams. It's the opposite of what's going on here. In here, the exam will not be a big deal if there is one. So what we're gonna do first, I don't have this all done, so I need another day or so to work on the homework. I'm gonna give you a bunch of data sets, and we're gonna start doing what's called data exploration. Now, we're not gonna be able to do all kinds of explorations because we need to move on in other things. Our purpose is breadth in this class rather than depth. We're not gonna pick a subject and go super deep in it. Rather, we're gonna have 6 subjects and we try to do a uniform coverage, so to give you an introduction of everything that you need to know as a foundation for other data classes. In here, the biggest deal is 2 parts. You're going to have to download these data sets. I mean, I'm going to put them online locally, so you don't have to dig them up from the internet. But they are in very random formats. There's some images in there, and there's some text data sets in there, and text is in raw form. There's really the news articles from Reuters like 20 years ago. So you're going to have a web page, or you're going to have a piece of text. So what's going to happen, you're going to have to write some sort of parser to manage that data. And we're going to discuss a little bit about what that parser should be, but it's your job to write the code that manages the data and puts it into a format that we call machine learning friendly. See, all machine learning and data mining does not work on raw data. It doesn't take bits and pixels and words and stuff like that. We need to transform it into a reasonable format that we can do what we want to do with it. That's our first assignment. Now, once we have that in that nice numerical format, I want you to think of the format we want as a matrix. I'm going to draw it on the board here in a little bit. So once we have the matrix format or the numerical format of the data, we can do simple stuff. So the simple stuff that we're going to do here, again, I didn't quite write down those problems, but by the time you get to this, parse the data sets, this is going to be all flashed out tonight. We're going to do 2 things. So in homework 1, let me start from here. We're going to have data parsing, normalization. This is different for different data sets. You're not going to be able to write a script that works on all 5 data sets because images are very different than text. Even though the output might be a matrix that looks similar conceptually, row versus columns, that's what we want, you're going to need different parsers for different data sets. I think I exaggerated here with 6 data sets. Probably I'll keep just 3 of them and do 2 of them maybe extra credit for those very good students that want to learn more. So I'll do 3 of them mandatory and 2 other data sets just for people who have more time and want to think about interesting questions. Some of these data sets will be not big, but reasonably challenging. So I think one of them is 2 gigabytes of text. Parsing 2 gigabytes of text on your laptop, it's not a trivial thing. I know it's not hard, I know you can certainly do it. How much memory you have? 16 GB or something like that? Right. So 16 GB, obviously I can parse 2 GB of text. But there are quite a few naive ways of doing it that will take much longer than it needs to take. So I think an efficient piece of code maybe will run in 2-3 minutes on that data set, 2 GB, while a naive one may take 10 hours to run. So how you do it, what language you use, how you define your internal data structure. A parser obviously will have some internal data structure that stores what it parses, right? As I process the text, I'll have to store what I've seen there. If I process images, I have to store what I see in there. And then when I output this, there are different options for what I want to output. We're going to talk about that in a second. So that's part one, if you like. Then will be a little bit of mining, toyish version. That is frequent items, and association rules. Let's put another one, association rules. Those are simple questions that are going to be specific, as in, what is the relation between a word and another word? How often they co-occur in text? Like Virgil is my first name and Pavlu is my last name. I could ask, how often do I see Virgil and Pavlu reasonably close in text, right? By reasonably close, I may mean within a window of, say, 5 words. Right? So you have to realize that answering a question like this, like a co-occurrence, or we call that a bigram, may not be enough to parse naively. If you parse naively and you just keep track of counts, how often Virgil appears in text, that's not going to give you how often appears next to another word. So you have to think a little bit, okay, how do I parse this data to answer that kind of question? Again, this is not hard. We're talking of programs that in Python will take 5 to 10 lines of code if you know how to do it. But it's not necessarily obvious how to do that. If you just keep the counts of words in text, you're not going to be able to answer immediate co-occurrence, right? How many people with me? Hands up so I can see. How many people are following me what I'm saying? Please, hands up. Okay. You should stop me when you're not following me. Okay. And we're going to talk about similarity and KNN. That's again toyish, very, very basic notion. We're going to use KNN, which is a supervised machine learning task. Let's write that here, supervised ML, which is not our job, this term. Supervised machine learning is not our job, but we're going to use that task as a justification for why we do parsing, normalization, feature analysis, so on and so forth. Because we're going to do this analysis on data, and then we have to show that what we've done makes sense, right? We're going to say extract features, or do dimensionality reduction, reduce the data set from 10,000 features to 100 features, right? How everything we do, we have to be able to evaluate somehow to tell, okay, it worked, right? Just outputting something doesn't mean it's good. So this is going to be one of the tasks that we're going to say, okay, how did that work, what we just done? This is going to be our evaluation methodology for some things. Okay, so we're going to implement it with the package if you like, but this is a very simple thing. And then whatever we do, we're going to say, okay, testing KNN, how that works.
So with the association rule finding, I learned that it is used for market basket analysis where you have transactions and you find frequent items.
Right.
So you mentioned that we use those to find how close the words appear, so there is no sense of transactions.
Right. There's 2 examples. So I use this in a loose sense. There is the transaction settings that I think it's part of the data mining book, and we're going to talk about that probably Thursday. But there's also the general idea of if you have 2 features, like 2 words, how correlated they are in general. And we're going to define a similar thing for images. What kind part of an image matters for the task that you have at hand? Because in images, there are different kind of images. The images that you're going to have here are images of digits. I think you've seen this data set before, MNIST data set. Every image is a 26 by 26 with some digit in it, like 0 to 9. what parts of image matter to distinguish the digit is different than if I ask, here's a picture in a zoo, what animal is in it? That's a much harder question. So that's what's going to happen in homework 1, roughly, and I still have to trim those data sets. I want to point out one thing that's much more important than people think. This similarity is as good as anything in data and analysis, data mining, and machine learning. In most classes that you take, you study that as a side thing, if you'd like. You get two objects, like two images, right? Once we're done with the parsing, those objects are in a matrix format now. So every image or every piece of text, it's a vector of numbers, right? How many people have seen this idea that I take my objects, images, people, text, whatever, and I transform it into a vector of numbers? Hands up. So I'm assuming people who did not have their hands up did not work with any piece of data that objects were represented as a vector of numbers. This is the first thing that we need to do in all data sciences. Take whatever data we have, could be patients in a hospital, lab tests, could be emails, could be web pages, could be images, whatever it is, and transform it into a numerical format that says, okay, here are values or coordinates or attributes, 1, 2, whatever, and each attribute has some value for my image. If an image is, for example, 26 by 26, that will be 26 times 26 pixels. So I've got right there, how much is 26 by 26? 676? Is that right? I think so. So I have 676 features, and each feature is some numerical value of the pixel. Pixel are colors, right? So there's so many options for the colors of the pixel. If my image is black and white, then every pixel has 2 values, 0 or 1. But if those are gray images, every pixel would be now between 0 and 255. Now if they're color images, I have an RGB schema, and now each R, G, and B is 0 to 255. The possible value of the values for a pixel is 255 times 255 times 255, right? Nice. Okay, I'm gonna have to call these guys and or just find a way to stack it somehow. So if I have an RGB image and every pixel has 3 values for colors, and every R, G, and B is between 0 and 255, how many options I have for a pixel? That'll be 255 cube option. That's a lot of options for a pixel, right? So I think you have to think of these numerical formats that way. Let's draw that matrix here. So before I have a bunch of introductory slides. The matrix format. We call this dense or full. Okay, I'll put it back in a second. Looks like that. This is conceptually. We can say this is feature 1, feature 2, up to feature D. And this is object 1, say x1, x2, up to xn. These are my documents or my images or my patients, whatever I have, movies, any objects I have. And in here, x1, I can write it as x11, x12, up to x1d. That is the feature vector. The feature vector for object x1. Yes, there was a question?
I'm not as familiar with CNN, but for convolution neural network, they don't necessarily make it into a vector, right? They actually feed it directly in the whole image or like something like that.
Yeah, but what you feed, if you feed, you mean if you feed the pixels,
Right.
that you can think of it as a vector, right? Even though it's a matrix, an image is a matrix, when they get fitted in the input layer, it's effectively feeding all pixels. Now, it's not that simple with images and neural networks. There's a bunch of layers typically that control the feature processing. So, why is your question about neural network?
So because I thought, so you said because everything needs to be represented as a vector.
Yeah.
For neural network, something like CNN, we don't necessarily.
But why are you asking specifically about neural networks?
Because I was familiar with only CNN and they did not actually
Okay.
make it vectorization of.
Okay, so I think they use something like recurrent neural networks or convolution neural networks to deal with the pixels.
Right.
And you can think of it as a vector. There are some other processing steps that people do. I want to make two clarifications about that because I'm not sure why he has the question. This doesn't stand for neural network here. I hope that's clear. What does it stand for? Nearest neighbor. It's unfortunate that it's very similar with neural network. We're not going to use neural networks as an object of evaluation, but I do plan to have a task for you guys that will force you into setting up what's called TensorFlow. TensorFlow is a particular neural network code put up by Google. And while you not have to program the network optimization, you have to set it up. You're going to have to write the Python piece of code that sets up the TensorFlow to do what we want to do. So you're going to run TensorFlow, install it and run it, but the internals of a neural network, the optimization, it's quite difficult, even for the machine learning class, let alone for this class. Okay? So in principle, I'm not going to say this is 100% all the time what's happening, but most of the time when people say feature matrix, they mean here are my objects, emails, patients, web documents, images, whatever I have, and here are my features. And typically this is a consistent set, as in every single object has the same features. So what happens for text? What would be F1, F2 up to FD if my data is text?
Words, vocabulary.
Words. So how many words will be here?
The vocabulary depends on.
In English, how many words will I have? I could have a small data set, Common English, 20,000 words, but if I really look at the dictionary, how many words are in English, I may have 500,000 words. And what would be those feature values? I'm going to say this is a feature value. Could be the count, how many times this word appears in this document, or what else? It could be 0, 1, right? It could be binary, which is what?
Exists or not
Exists or not exists, right? What other features can I have here for text if I want to go beyond words?
Index values.
Hmm?
Index values,
What's an index value?
like where it appears, its position in
I could have some sort of positioning, not just how many times the term appears, but is it in the title, is it in the body, is it in a link, something like that. What else can I have as features?
Some kind of similarity there, scoring, figure scoring.
Like what?
Dictionary or this comparing to some other dictionary.
Right, if I have special features that are, this is process features. I could have, for example, relevance to a question. Is this document about President Roosevelt? In particular, I care for my task about President Roosevelt, so I'm going to have some sort of process feature that's not simply related to the document in terms of words, but is related to the task. Is this document, how relevant is this document for the topic of President Roosevelt, or for the topic of Catholic Church, for example, right? And that's where information retrieval comes into play. To answer how relevant a document is for a particular topic like that, we need a class that's information retrieval. A large part of information retrieval figures out how do you compute a score like that? How do you know? You can look for President Roosevelt in text if you like, and you're gonna see, you know, how often that occurs, but that's not good enough. In information retrieval, their job is to, once you have process features, to say, okay, what quantity should I put here? How good is that document for that topic, right? Or I could also have, like in collaborative filtering, like Netflix. Netflix has this, say, those are the movies, right? And their features might be the genre, the, you know, box office, principal actors, is Brad Pitt in the movie or not? Or principal directors, or all kinds of, does it have naked women? Does it have bombs and explosions? What does it have, right? Because Netflix care about some features that they can match different users with different profiles with the movies, right? So some people like explosions, they want to know is a movie with action and explosions or not. But they also have user ratings, right? So you can imagine for a movie, I have the movie features, what's up with that movie, what's the genre, what's the length, what's the size, you know, is there crying in a movie, are there bombs, whatever. That's purely up to the movie. That's what's in the movie, right? But then I have users like Virgil, which rates the movie a 4. That's very subjective, because that's not anymore just about the movie. That's the movie for me. I may rate it a 4 and you rate it a 2, right? Could happen. It happens all the time. By the way, my ratings are the exact opposite of my mom's ratings. Every time my mom says she likes a movie, that's a super strong indication I'm not gonna like it. And every time I like a movie, my mom will never watch it. Okay? So that's a subjective rating now. It's not about the movie alone, right? Like I like Game of Thrones because I like dragons flying around, and my mom hates that kind of stuff. So now in that data set for Netflix purposes, which is recommendation system, how to know what movie to recommend me, there are the pure data features, but there's also subjective features like what users like what. So that's a new problem now. How do you deal with that part of the feature matrix, that are user ratings? And users could be many, right? Netflix has 70 million users. That's a lot of users to deal with. Another thing that I want to say here is the formats of this matrix is essential. Now, for the data sets you have, you probably can do almost anything and make it work. But in practice, how you manage these formats is very, very important. Most of the matrices that you're going to need in practice, again, I'm not saying for this homework, in particular, if you have a desktop computer with a decent amount of RAM and CPU, anything you want to do on these data sets is going to work because they're small. But in practice, sparsity is a big factor here. That is, by sparsity, even if you don't know linear algebra, I mean, most of the values are 0 for a lot of features. Especially, the more features you have, the more likely is that a lot of them are 0. Because think about it, if those are bigrams, bigrams are pairs of words. Instead of 30,000 words or features or 50,000, bigrams could easily be 1,000,000 bigrams because I'm pairing up now a lot of words, right? But the more features I have means that less likely are they to occur in text, right? Because I still have only 20,000 documents or 50,000 documents. If I have 1,000,000 features, that means most of them will never appear in documents, or if it appear in only one document, right? So these matrices, the more they are wide, the more columns they have, the more zeros are inside. So we have to deal with those zeros somehow efficiently. That's where a lot of computer science coming in. Algorithms and data structures. How do we process the matrix, how to make use of it. Now, the fewer we have, when we talk about dimensionality reduction, for example, that's like module 3, I believe, we're not going to have that many. We're going to transform a data set from 20,000 features into 200 features. When we have 200 features, of course, they're going to be very dense, right? Because if I manage to represent a data set that will be the same images or the same documents that are the rows into only 200 features, there is no way those will be sparse to have zeros. They'll have to have a lot of real values in there to have the same representation power. So the sparsity is not an issue for few features, but it's an issue when you have a lot of features. Now, some machine learning algorithms are far more suitable for long set of features, and some machine learning algorithms are more suitable for shorter set of features. Now, before I move on with some slides here, which I'm going to go through quickly, let me turn this on. I want to talk for a moment about, on the first module you have, why is similarity so important? There's been recently a proof that similarity is equivalent to solving any machine learning problem. Ability to understand how similar objects are. For example, two patients. If I could tell for every single two patients, right, how similar they are in a correct way, correct in a mathematical sense, we'll get to that. That's equivalent to solving any sort of classification or regression or data analysis problem. In fact, in machine learning, in the last 10 years or so, has been a lot of emphasis into what's called dual problems. People have studied regression or support vector machines, and then now they come up with the dual optimization problem. And these dual problems, they're all based on similarity notions. So let's suppose we call this matrix X, big X. What is X times X transpose? So let's think about that. How big is this? This is N times D, roughly, right? Sometimes in a machine learning supervised, what's the difference between supervised and unsupervised? Common sense, I mean.
You know metric or visual optimization?
No.
Unsupervised machine learning is basically for classification or finding out patterns, and whereas in supervised machine learning we basically answer questions. Questions are already given. We
No.
are
So
trying
for
to find out.
supervised, we have training data set, and we have the label associated with each problem.
Yeah, this is the second part. That's the answer. Supervised machine learning. Typically, I'm talking about common sense. Don't take me to judges. I'm talking about common sense intuition. In supervised machine learning, we typically have labels for the task we care about. Labels, as in, suppose I have patients. I want to know if they have diabetes or not. This has to do with the age of the patient, the behavior, the blood test, the temperature, blah, 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 everything I know about that person. But what's the label if I care about diabetes?
Yes, sir.
Has diabetes or doesn't have diabetes? Sometimes it's not yes or no. Sometimes it's a gradation. Many diseases, including diabetes, is not a black and white thing. It's no diabetes at all, that's great. And up to when you have, I don't know, level 4 diabetes, you're about to die very soon. But there's some things in between, right? They measure the sugar composition in your blood and how well your liver and your heart works. And there is, pre-diabetes, high sugar, stage 1, stage 2. So in many cases, there's not a black and white thing. It's a gradation. Even that, it's a label, right? At what stage are you in this process? Or any patient, right? So labels are, of course, data-based. Label is directly associated with the patient in this case. But I could have, for the same patient, different labels in a different context, right? If the same person who has been to the hospital and checked his diabetes, and he has a label for diabetes, say it's stage 1. The same person that goes to Netflix or something has a preference for what movie they want to see. From a Netflix perspective, they don't care about diabetes, right? They care about what kind of movies or what kind of TV show this person is about to want to watch next. That's a different label. That applies to the same person, but in a very different context, in a very different task. So labels are not simply, sometimes we have the column here, label, that means supervise. Label is not purely related to the data. It's a combination between data and the task you want to perform, classified or regression or something, right? So the biggest distinction between supervised and unsupervised machine learning is that in supervised machine learning, we have those labels for the training set, right? So we learn the patterns that we want to learn, for example, how to predict diabetes for patients. Having access to the features, which we already have, even in an unsupervised machine learning, we have the features all the time. X is available. But in unsupervised machine learning, we typically do not have labels. So we can't answer specific questions like, is this person going to have diabetes, or predict diabetes, or model diabetes? Because for that, we would need patients that have diabetes. We would need labels. In an unsupervised machine learning, we don't have that. We typically have X matrix. So we cannot answer specific questions like what movie this person's gonna like necessarily. Maybe we can, but there'll be some specific questions for which we're gonna need training data with labels that makes it a supervised machine learning problem. So for that, 6140, the machine learning class, is the one to take. Now, we can still do X times X transpose, right? I mean, for X, do this matrix multiplication, we don't need labels. So what's the dimensionality of this? ND times DN, right? Everybody knows what transpose means? What does it mean?
Rows one.
Flip it over the main diagonal, right? So now, of course, if this is N rows and D columns, that's D rows and N columns. What's the size of this whole thing once I make the product? N times N. Sometimes we call this K for the word kernel. Sometimes we just call it similarity matrix. Okay. So this K, if I want to look at it, it's going to be 1 to N, 1 to N. So if I pick an object I and an object J here, this is Kij, right? In this matrix, that's the product. What is Kij? In a algebraic sense. How did I compute this value Kij? I mean, what happened here to get a particular value of K?
We did IO and multiply some.
So what happened, I took the xi, the row, right? So I took the xi was here, that's the row. And I multiply with what? The column, what's the column in the transpose matrix? What's the J column? Is row I times column J, right?
Yeah.
How many people familiar with matrix multiplication? Hands up. That's something you have to know. I mean, if you don't know it, you should go home today and figure out how matrix multiplication works. Okay? So this is a row I from here and column J from here. Well, what's column J really in here? Is the same xj, right? Because big transpose now it's a column. So this is really xi times xj. It's called a dot product, right? So that's the basics of how matrix multiplication works. It takes a row and a column. And actually, I want to write it down to the bits to make sure we understand what dot product means. It's a sum for all components, right? The components, how many components are there in each one of these vectors? D. So from maybe D equal 1 to big D, it's xid times xjd, right? It's first product, second with second product, third with third product, teeth with teeth product, add them up. That's the dot product between two vectors. We're gonna need dot products, and once we have dot products, how to multiply matrices. That's gonna be necessary. Okay. Is this a similarity notion? Can I take this Kij and say, if it's big, it means something. If it's small, it means something else.
It's cosine distance.
Right. But before we go to cosine, why this Kij? What's the intuition behind Kij indicative of, say, similarity? Why is it that a high Kij? What's the difference? When do I get a high Kij, and when do I get a low Kij? Now, to answer those questions, let's assume I have normalization. So let's assume, we're going to talk later about how to normalize data, but let's assume all xi's, all feature values xid are, say, between -1 and +1. That's not necessarily true at the end of normalization. There's different kinds of normalizations, but for the purpose of answering this question, what's up with Kij, let's just say every single feature value in my matrix is between -1 and +1. And normalization gives some other benefits. It centers a certain column to 0, like the mean of every attribute is 0, stuff like that. We're going to talk about those later. For now, I want to ask the question, when do I get a very high Kij? What it will take to get a high Kij?
Both two rows are same.
Both are 1, 1, 3 at the max.
Let's give somebody else a chance, somebody who didn't talk yet. You did, somebody else. How do I multiply things to get a high Kij?
Both of them are exactly same, you get the highest.
I'm not sure that's true. Suppose both of them are a lot of zeros. Do I get a high Kij if all of them are zeros? How do I need to multiply things? I'm talking about mathematically, pure mechanical, not in terms of conceptual.
Ix value and the J's value, if both have big numbers, right? If we take it in terms of two documents, if the word X is coming 4 times in this also and in this document also, we will be multiplying, for that word only we will be multiplying, so the value of the dot product will increase for every particular word.
So I don't want to talk about documents, but your explanation is good. But I don't want to worry about documents right now. I just want to worry about numerical values. To get a high product, whatever xi has a big value, say in component d equal 22, xi has a big value, then xj needs to have also a big value. And every time xj or xi has a very small value, like -1 in some component, to get an overall high product, I need the other one to also have a very small value. So to get a high overall dot product, wherever one of them has small values, the other one also has small values. And whenever one of them has high values, the other one also has high values. Because small times small or big times big results in big overall. And if that happens for a lot of the components or the features, then overall I get the big product. In fact, the biggest value I can get is for when all of them are either -1 or +1. There's nothing in between. And every time when this is -1, that's -1. And every time when this is +1, that's also +1. That's how I get the maximum. Maximum being 1, 1, 1, 1 product, d times, that will be the maximum will be. So to get a high Kij in this sense, I need them to align, right? Because high values will correspond to high values, small values will correspond to small values. Now, if those values are words in a document, or blood tests, or age, or temperature, what it means in practice is that those objects are similar. Whenever it comes to age, if it's a young, the other person will also be young, right? Small values. If it's a blood test, you have high blood pressure, the other one must have high blood pressure, right? So a high Kij dot product, which corresponds, as somebody says, with a cosine distance. We're going to talk about that next time, exactly what it is. It's obtainable when both vectors have similar values. How about small Kijs? What's the recipe common sense recipe to get a very low Kij. It's the opposite. To get a low Kij, every time one has a low value, the other one is a high value, and every time this one has a high value, the other one is a low value. That way, I will never get high values, right? Because assuming it's centered in 0, every time I get a -1, the other one has a +1. I always get small products, right? So this is the basic notion of similarity we're going to look at, that is dot products. That's not the only one, so we're going to have to implement few measures of similarity. And for some algorithms, yes?
But if both vectors are 0, then showing the similarity is the highest.
If both vectors have 0 in this world, 0 is kind of undetermined, right? Imagine if I run patients, like I said, and every single value is 0. That means 0 means between -1 and 1, I don't have a strong indication either way, right? Suppose I do the blood test that has been normalized. It's not anymore between 0 and 70. It's between -1 and 1 after normalization. What's a 0? 0 means it's neither low or high.
But when
And-
you're talking about similarity, that means both these cases are equally undetermined. So even then the similarity should be the highest. So that case is very close to this case.
Yeah, yes, I think you're looking at a different distance. So we can talk about that too, how far away the values are, right? Because I think what he's concerned with is say, what if I look at my xi, xi1, xi, this is the entire vector, xi2 up to xid, right? And I look at xj1, xj2 up to xjd. What he's proposing, how about I do the difference? So in order to compute some sort of similarity or distance, similarity and distance are opposite notions of each other. So what he's saying, okay, how about I do here xi1 minus xj1, absolute value, say that's the distance. In here I do xi2 minus xj2, absolute value, all the way to xid minus xjd. Now I've got a vector of differences. In the example you give, if this is 0, 0, 0, that's 0, 0, 0, this is going to be perfect, like no difference at all. This is similar to what people call editing distance, right? And it's good sometimes. For some cases, editing distance is preferable to algebra. This is an algebraic, linear algebra distance. In most problems, however, especially when the data has been normalized, this is a much better indication of similarity. See, the common sense, I think, explanation, I'm a mathematician, so I may not be the best person to offer a concrete, practical explanation. But I think the explanation is this. If you normalize your data and you get 0, 0, 0, 0, you don't have any strong signal for whatever you want to do. So if two people have 0, 0, 0, 0, you could say they're the same, as in I can't tell anything about them. But then that doesn't make it similar for whatever task you have. If, on the other hand, you get a dot product that's very, very high, it means whatever blood test and age and you know, temperature and heartbeats, everything you measure for me is the same like for you. That makes a strong indication that if I have diabetes, he also has diabetes. You know, I think that's the common sense explanation. So I'm not saying the editing distance is not good. I think there'll be some cases when we're going to care about editing distance. But the standard distance in algebraic sense is that one.
I didn't follow why the other one is better compared to this, as in why the kernel stuff actually tool is better than the edit distance.
Because the edit distance, it's only good, it doesn't measure the magnitude of the values, right? It's exactly the 0, 0, 0 case that it's in between and it's not indicative of what you want. So in that sense, the kernel distance of the dot product, I think it's called dot product distance or cosine. I call it kernel for linear algebra purposes, but it's called cosine or actually for cosine we need a little bit normalization here of the vectors. But in that sense, this will only count as similar or dissimilar if you have high or low values.
So I think the first part is, I think we can tell that two unknowns cannot be equal, because we don't know two unknowns are.
Right, but how unknown is it? Is 0, 0, 0 really an unknown thing? That depends on the data you have. And that comes down to a different problem, which is, did you collect the right features for the task you have in mind? Because if you want to care about diabetes, but you collected completely irrelevant data, what suits color I wear, right? And whatever, where's my house and stuff like that, you're going to get a lot of zeros because some of these features are totally irrelevant to the task you have in mind. So this question of did you collect the right features that you need for the task you have in mind, that's not so much related to the processing and algebra, but related to the initial domain knowledge. A doctor will tell you what kind of blood test you need for diabetes. There's a different question? Hold on.
How much does normalization play a role in taking the dot product? Like if you don't normalize your data, how different would your...
Typically people do normalize it. Occasionally you have to look at this normalization to see if they make sense, because a lot of normalizations are done purely on mathematical frameworks like statistics, like zero normalization, zero mean unit variance, those sort of things. And sometimes you damage the data with that thing. So I think that's a standard assumption is that you're going to normalize data, but then you have to look to see if you lost something along the way. I don't know if we're going to be able to get into that, but on those data sets, we're going to try to have code available before you run it. So we're going to be able to answer the question, should I normalize the data or not?
And also, if you don't normalize it, the notion that you're going on, the high and high and small, that would...
Right, the cosine has an additional denominator thing. So we're going to talk more about those formulas later, so that even if you don't normalize, the cosine in a geometric sense depends only on the angle between the vectors. So even if you live in unnormalized, the angle, as long as the angle don't change, the cosine don't change. So we'll talk about that on Thursday.
So what if xj is 0.5, so the multiplication will be 0.25, so it will be less. So both are 0.5. So
You mean centered at 0 to 1 instead
no,
of...
no. If the value of xi and xj is 0.5,
Yeah.
so then the multiplication will be less than that. So it is indicating dissimilarity. Both are 0.5.
Why dissimilarity? Because the median, the average will be 0. 0.25 is still higher than 0, right? I think the random, when you can't say similar or dissimilar, will be on the whole dot product gives you a 0. Now, I know you guys want to learn everything in one day, but we have a third term, right, to talk about stuff. My plan is to give you a sort of overview now, related more to homework 1 than the rest of the term, of course, but I don't want to get into all the details at once. I do want to say one more thing, yes.
You talked about two approaches. One is dot approach, another one is the difference approach. So for the difference approach, you said that whenever we get a 0, we can't really say anything about like how are they two related, if a person has diabetes or not. But my point was, if the overall difference you get is 0, and if the first person has diabetes, it means the second person also has diabetes because they're similar.
The thing is, if I think in a common sense, I think that's the same question rephrased. If you get 0, 0, 0 and you have diabetes, it's not like the person has diabetes, but the features are not indicative of that.
But then can't we
Another person that has the same features is equally likely to have or not have diabetes, because you measure the wrong things about that person, like shoe size. You happen to have a patient with diabetes, but the features you have are not telling about diabetes. It's a random, it's not a correlation between the features and the diabetes. We're talking about a very concrete case. May not be true in all the data sets. What I'm pointing out is that even though you have a bunch of features and you have labels, diabetes or not, it doesn't mean necessarily that those features are indicative of diabetes if you collected the wrong features. Even though me and you have the same exact representation, we have the same exact features, if those features are not related to diabetes, maybe I have it and you don't. The features are not everything we know about patients. The features is what we collect, right? A doctor looks at the spreadsheet and say, blood test is this and that. It's quite common in hospitals, even today in the years 2018. They don't have the right feature. A very common problem in consulting, we're getting a lot of consulting requests, is, are my features good for what I want to do? I've collected those features and they don't seem to be telling me all the time what's going on with my patient. Very often the answer is you didn't collect the right features for that data. In particular for images, that's a hard problem. What should I collect for images to tell things like, is there a tiger in this picture or not? It's not obvious if I get all the pixels with pixel value with colors that I can answer the question, is there a tiger in the image or not, right? I need to collect other things like contour and contrast and background to be able to answer some questions. So I think a typical case when you can get the same exact features but different labels or different answers is that the features are not directly relevant to the problem you want to solve.
But if features are irrelevant, then no algorithm makes them, right? As in if-
Right. We need different features. So, but that's not quite true. If I have an image with all the pixels, I effectively have all the information about the image. There's no question about collection. I have all the information. But most algorithms have to process those features in a certain way. And if they don't get at the heart of the problem, is there a tiger or not, they can't solve it. That's why they need this convolutional neural networks. It's a very complicated framework because you can't tell in advance what features in the image you need. So a convolutional neural network effectively tries all kinds of squares until it figures out what parts of the image matter. So it's an entire machine learning algorithm just to figure out what parts of the image are going to be good for that task. Because you can't tell in advance just by the pixels. Now that's different than the patient problem where they don't want to spend money to collect everything about you. There's thousands of tests that they can do in a hospital, but they only want to do the ones that are pertinent to what you might have. So their question is a financial one. I don't want to spend the money doing x-rays to your legs if I believe you have a heart problem, you know? So how do I know I collected the information I need?
Shouldn't we first filter the features first? Only the relevant features.
How do you know what's relevant?
If you talk about diabetes, the shoe size doesn't matter, right?
Yeah, that's assuming domain knowledge. That's assuming the doctor, somebody has to tell you that, right? I mean, that's an extreme example, but obviously shoe size may not matter for diabetes, but there are some really gray areas where you may think, even myself, that's a true story. I've had a ankle, hard time to walk, and ankle got swollen and stuff, right? I was sure it's some sort of mechanical bone problem. Maybe I hit my leg into something and it got swollen. I was sure. I went to 3 doctors. True stories, I'm not lying. That was in 2013. And they all look at my leg, analyze it, took a blood sample, x-rays on what's going on, until they sent me to an expert. I remember I had to go to MGH at the Boston, and they, as long as the guy saw my ankle, says, you have a lung problem. What? You have a lung problem. This is not related to your bones. It's related to your lungs. Now, I think that's an example where you clearly need domain knowledge to know that the test you want to do is on lungs, not on bones, right? And there's many gray areas like this on pictures. And what's true? My problem was with lungs, not with the bones. So he gave me the right medicine and all that, so I'm fine, right? But in many gray areas, it's hard to tell in advance what features do you need, right? And even if you have the label, I mean, there's a lot of machine learning that's concerned with that problem. If I have the labels, tell me what features do I need. But sometimes domain knowledge is key. In text, for example, how do I know I need bigrams or not? Extracting bigram is a huge effort compared to just words, right? And matching bigrams. There's entire systems developed just to how to extract bigram values. How do I know if I need them or not? I need some domain knowledge to know that the task I'm looking for, say, sentiment analysis, relates more to bigrams. Like if I want to know how you feel about the movie when you write a review, it turns out bigrams are the real deal. Because if you look at pairs of words that occur close, people say, waste time. It's a strong indicative that the movie was bad, you know? So in sentiment analysis, bigram matters, but for, but for many other things, bigrams do not matter. I didn't get to my slides. Yes, that's good.
So are you trying to imply that dot product is more tolerant to irrelevant features?
I'm trying to imply that people like mathematics, they like to show off, and dot products are very nice with mathematics. extremely nice, as in much nicer than other things. Because linear algebra, if you can keep it as linear algebra, not quadratic forms, not optimization, just linear algebra, it's a very powerful mathematical framework and programming framework too. We can do things in linear algebra, things like eigenvectors, for example, or dimensional reductions very, very quickly, if we can keep it at that. So in a linear algebraic sense, mathematical sense, dot product are favorites. Here's an example of that. How many people know of a rank of a matrix? What's a rank of a matrix? Yes.
So it's the number of non-zero rows of columns after you've done your.
Right, that's procedural, but conceptually, what's the rank of a matrix? Number of?
Independent rows.
Right, independent rows and columns. So if I look at this K in a data set, this is n by n, right? N by n is a gigantic thing. Even a simple data set might have 50,000 points. It's like some of the data sets I give you, I think they have 200,000 articles. So this is 200,000 times 200,000, right? Now, it turns out the rank of these matrices are a lot smaller than n. Theoretically, a square matrix, what's the biggest rank that it can have? N. In practice, of course, this is much smaller than n. The rank of that matrix effectively tells me how many internal dimensions I need to represent my data. Even if it's 200,000 by 200,000, if the rank is 20, it means the same data can be represented in 20D. Because it means there is a decomposition of this with only 20 columns that achieves the same similarity. Now that's pure linear algebra. It doesn't say you have patients or you have images or you have documents. It only says if the rank of this matrix is small, you could have represented your data with a lot fewer D's than you have, perhaps. So that's one example where linear algebra comes really handy. Will tell you how many dimensions you actually need. And PCA will tell you how to get them. I'm not saying it fits all the data sets. All I'm saying is it's nice to work with mathematically. So we're not gonna, I don't want to give you the impression that we're gonna do only this. Your part of homework 1 will be a bunch of similarity matrix. And for different data sets, I'm gonna ask for different things. I wasn't planning for editing distance, but now that you guys said it, I can add it to the homework. What are the two main distances that everybody knows about? One is, one is the cosine or dot product. Cosine is really disnormalized by the norms. What's the other one? Euclidean distance. What's Euclidean distance? How do I do? So this is really a similarity or a distance. Similarities are measures that high means more similar, more the same, and low means dissimilar. Distances are opposite. High distance means the objects were not the same, right? And low distance means the objects were close. So what is the Euclidean distance? Between my objects xi and xj. How do I compute it? So sum of, for all components d from 1 to d, right? xid minus xjd. Now I can take a square root if I want to. This is the square form. If I take the square root of it, I get the length of the vector, right? So in a geometrical format, if this is xi and this is xj, who's this? If I take the square root of it, the length of?
Line x.
So this line here, the distance from here to here in geometry will be the square root of the Euclidean distance. Right? Now, this is a distance. I know it sounds obvious when I said it, but this is a distance. The distance is the opposite of a similarity, right? If those two are very similar patients, Like high values correspond to high values and low values, what be the distance? Zero. And if they are very dissimilar patients, small values correspond to high values, the distance will be high. That's the opposite of similarity. Right? Now, in this particular distance, what's the minimum that can be obtained? Zero, right? Because sum of squares, whatever you do, you can't get below zero. So the main two distances that everybody is using are Euclidean distance and cosine distance. But if you were to look for distances, they're probably like 200. Okay? We're not going to do all 200, but we're going to do a good bunch of them. And the last point, I didn't get my slides. I'll post them online, and we'll recap them next time. It's blah, blah, blah anyway. You don't need all that. What I want to emphasize that most people don't know, even after they finish machine learning and data mining, is that ability to have this is as good as anything. All this algorithm, like fancy neural networks, support vector machines, all of that, if instead of doing that, one can compute a good similarity for that task, that will solve any machine learning problem. Imagine, I have a very hard problem, diabetes prediction, right? What is a hard problem in the machine learning sense? I can find an easy model that transforms my features into a prediction, right? Any sort of model like a neural network or a support vector machine will look at my feature values and will have a model function. A regression takes those values and multiply with certain coefficients, gives a score, and then thresholds that score, right? If it's bigger than something, you have diabetes. If it's smaller than that, you don't have it. And regression job is to compute the right coefficient for each feature, right? How many people heard of linear regression? Some of you. In a decision tree, we look and say, if this is smaller than something, this particular value, add a value to my score. And if it's this smaller than something, subtract the value, and add and subtract, follow different paths. Eventually I get somewhere and I say, if you have that path, smaller than this, bigger than that, smaller than this, smaller than that, so on and so forth, I go through the features, I conclude, my tree concludes you have diabetes or you don't have diabetes, right? Naive Bayes works in a certain way too. The point is, suppose I have a hard time doing that. Suppose there's no way for me to implement a decision tree, a support vector machine, a neural network, a regression. Doesn't seem to work. There's a theorem that says, imagine I can compute very good similarity. Somehow I have a similarity, either the dot product or the Euclidean distance or the editing distance, that somehow, magically, everybody with diabetes become very similar. The similarity is a number, right? This Kij is a number. Suppose I invent a metric that somehow looks at the two patients, and if they have both diabetes, they end up very similar. And if they don't have diabetes, both of them, they end up very similar. And if one of them has diabetes and the other one doesn't have diabetes, Kij is a bigger value. If I do distances, will be the opposite, right? If they both have it or not have it, this will be very small, because it's a distance. And if one has it and one doesn't have it, this will be high. Suppose I have this Kij. It will be trivial to do the classification. If I have a similarity that groups somehow together the people with diabetes and the people without diabetes, doing the classification will be a piece of cake. So there's a theorem that says the hard time on a primal problem like training a support vector machine or a decision tree or a naive Bayes or a neural network, it's equivalent or it's not harder than getting a good similarity function. If you can define a similarity function for your objects, images, or patients, or emails, such that any two emails that are spam are similar, any two emails that are not spam are similar, and any spam with non-spam, it's not so similar, means you've got the perfect classifier right there in your hands. Once you have a good similarity function, you can solve any machine learning problem. This is something that's not well understood, that defining a similarity function, it's equivalent to solving data problems. And sometimes it requires domain expert knowledge. Sometimes a doctor can tell you what makes two patients similar in a way that you cannot easily learn it from data. Because the doctors have this heuristic that they've learned over 2,000 years of doing medicine. If you have this, but not that, but this, but that, there's something going on with your lungs, and then you're the same like him. I didn't know that, right? So sometimes defining a similarity requires some domain knowledge, but if you have a good similarity function, bingo, you can solve any problem. That corresponds to what the machine learning calls duality. The primal function is training a classifier on the data. The dual requires a similarity, and it does exactly the same job. Now, we didn't get to the parts that we want to get, but that's good. It's a good introduction. We have some setup for the homework. I'll edit the homework, so please, no questions about the homeworks until tomorrow night. Why? Where's the data? Why I can find it? Why it's not written well? Because I need another day to fix that homework. But please do the two things. Register on Piazza, and we need to share a Dropbox folder, not with virtualpowerplug@yahoo.com, but there is an account for this class. All right? And we'll announce office hours. I think the first office hours might happen Wednesday or Thursday. My intention is to have them every day, even Saturdays if we need to. All righty. Sure. Let me shut this down.